Hello and welcome to part 3 of lecture 2 of ENGR 2301 Engineering Statics. In this portion of the lecture we are going to look at vector operations, namely vector addition and vector subtraction. So we're not going to look at, say, cross product and dot product yet. We'll see those in later lectures. But today we're going to be looking at, or in this portion of the lecture, we're going to be looking at vector addition and subtraction for simple 2D vectors in both polar and rectangular form. So let us consider vector operations. What do we mean by this? What is meant by vector operations? And in particular, let us first consider vector addition, because that's really the more fundamental one. Vector addition. Well, what fundamentally this represents is the summation or the combination of one vector onto another, or one vector with another. Of one vector with another. With another. And this is a way of summation that preserves the directionality of vectors. Unlike simply summing the magnitudes like you would have, say, with summing, scalars, when you do proper vector addition, the directionality of the combined vectors is preserved. The directionality of vectors. So it preserves the directionality of vectors. Okay, so that's vector addition, or that is the basic idea of it, the combination of it. So let me give you some examples of what this means. So let us say that I have a variety of forces acting on a single object. So let's say I have an object that we could model as a point particle, and let us say that I have a variety of 2D vectors applied to this, maybe F1, F2, and F3. And F3. And I am concerned, or I want to know, the net force applied to this particle, or this object, and I could find this by applying vector addition. And what I would want to find is a single F net, or net force, that represents the summation, the vector summation of all of these. And again, this is something you probably are familiar with, or hopefully are familiar with, from earlier courses, but I'm just spelling it out again and reviewing it in perhaps greater detail than what you've seen before. So F net, if I'm looking at forces, is the combination or the net effect on the point particle, or the net effect on the object, from all of the individual forces applied to it. Applied to the object. So if I were to consider a very simple example, an extremely simple example, let us look at something that's almost so simple it's almost a scalar problem. Well, net force, of course. If I have F1 to the left, that has a magnitude of, say, F1 has a magnitude of, say, I don't know, maybe 2 newtons. And F2 to the right has a magnitude of 4 newtons. Again, this is so simple it's almost a scalar problem. The net force of this is going to be a 2 Newton force to the right. And of course, that's a relatively trivial example, but we'll see more complex examples herein. So, and we could also do this for velocities, we can do this for accelerations, etc. Or we can even do this for things that aren't even directly applicable to statics at all. I could talk about things like, let's say I have, I could even look at this in terms of, now again, for most of the vectors we're going to deal with in statics, we're dealing with things like forces. and not accelerations even, because this is statics class. But let's say I had something well beyond this course, but not something I think you haven't encountered yet. Let's say I had two electric fields. Let's look at something really different than statics. Let's say I had one electric field. An electric field 1 produced by maybe two sets of parallel plates. Maybe there's a I'm going to borrow some material from electromagnetism here. Let's say there is a, electric field describes how positive charge travels. That's from positive to negative. So there's one set of positive plates here, and another set of, or a set of negative plates here, or just a single negative plate here. And this E1 vector is, I don't know, maybe 5 newtons per coulomb to the right. And then there is another set of plates. Maybe there is a positive plate here. And there is maybe I'll do this in a different color actually to illustrate the contrast between them. There is another set of plates in the vertical or horizontal depending on your perspective, but the field will be pointing vertically. The plates will be horizontal. And this would have an electric field downward. Now, you don't need to know anything about electric fields for this course, but this is just an example to illustrate how diverse, how diverse and how flexible the ideas of vectors really are. So this is something that has absolutely nothing to do with statics class, but we can use the principles of vectors for something like this. Let's say we have an E2 is equal to, 2 newtons per coulomb or something. What if I wanted to find the net electric field on an object placed in the middle of this, a charge placed in the middle of this? What is the net electric field? Well, I could do this by a simple vector summation, very trivial, simple vector summation. So I would have an E1 equals 5, and that would be going to the right, and an E2 downward of 2 equal to 2. And that would have magnitude of units of newtons per coulomb, and E2 downward of 2 newtons per coulomb. And that would have some magnitude and direction, some theta, and an E net magnitude. Fairly straightforward, although we're going to look at how to apply some of the principles of vector addition to more complex systems in a bit. This one is trivial because it's all laid out already basically in component form, so this connects very well with some previous things we've seen in part 2. It's basically just a problem of converting rectangular to polar. But I'm just providing this as an example of where you might use vector addition on things that are very far removed even from static class. But this is also an example of where you probably have seen vector addition before. I am assuming this is not the first time you have seen vector addition. I'm covering this at a brief and basic level, but again, I'm hoping this is not the first time you have seen this. I'm using this more as a refresher, because again, some of the students who've taken statics, sometimes students take very meandering paths. Not everyone goes straight from, actually, especially nowadays, many students don't take the very traditional, they finish their senior year of high school and they go directly into, introduction to engineering and Calculus 1 their first semester out of high school, and Calculus 2 their second semester, and then literally just, 3 semesters after high school they're taking engineering statics, and that's kind of the traditional straight out of high school path. But especially nowadays, many students are taking very divergent paths. Maybe they work a few years, maybe they do their degree part-time and then take a couple courses a semester, etc., etc., etc. We could go through the permutations all day long. So I am trying to accommodate students of all sorts of different backgrounds in this course. But anyway, let's look at how you actually sum vectors. And I need to discuss this in a framework of 2 different methods, and that is what we've seen previously. That is both the polar and the rectangular. So we'll have different methods whether we're trying to sum things either polar or rectangular. So vector summation, we can break this down into methods that are applicable to the polar or the rectangular. Or rectangular. Or / Cartesian. So let us consider polar vector summation. And there are two big methods that we might use. The first one I will cover only briefly because it's almost impossible for me to do in the format of these lectures that I'm doing. I would need to do this accurately. I would need to use a document camera and a ruler and a protractor and make all of my drawings exactly to scale, or as exact as I can. And that is a graphical method. I'm not going to spend much time on this, but in olden days, especially before the advent of nice portable calculators, hand calculators, this was actually a fairly common method of doing vector summation. Graphical methods. So let us say I have several forces applied to a particle. Let's say I have a particle and there are several forces applied to it, and I want to find the net force on it. So there's an F1, and let me draw some components here, or sorry, some axes here. X and Y. And let me just label this F1, F2, and F3. Actually, maybe more like F2, and let me just put F3 out to here so I can be a little more flexible with my quadrants. And I had 3 corresponding angles. Maybe I'll draw that a little bit closer in. A theta 1, a theta 2, and a really large theta 3. And I wanted to find the combined net force on this. Well, what I could do is, I could literally do this by hand. I could sit here with pen and paper, or probably pencil, and eraser, and a nice set of graphing paper, and more appropriately, a very nice ruler, a straight edge, and a protractor, and I could literally, pen and paper, do this by hand. So if I wanted to do this by hand via graphical methods, what I would do is, let's see. Let's create this, let's do a nice big set of coordinate axes. Again, using the kind of methods I use for my lectures here, my video recordings, it is really impossible to do this to truly demonstrate a graphical method. In fact, even in a physical classroom on a whiteboard, it is really impossible to truly demonstrate this. You really need to use a protractor and a straight edge, and not just a straight edge, but a ruler to measure these distances properly, because in basically all, now this is unstated from my previous videos, but really there is an unstated thing in all of the drawings I use throughout my entire courses, and this is very common in all sorts of science and engineering courses, that I never really draw my drawings to scale. It's not really important for most of the things I do, but if you are using a graphical method to solve a problem, scale is everything. So you need to make sure everything is to scale. And so that's the real pain. This is why this is really a pain in the butt, especially in the era of modern hand calculators. Now, if you were sitting here in 1930 and you were trying to find the net force on an object, or some vectors up, graphical methods were great because really they were one of the few tools you had. I suppose slide rules are available. I mean, you could use slide rules, but between and also sine tables and cosine tables and things like that. But compared to the convenience of using a calculator, if I have to use a slide rule and a cosine table or a cosine book or something like that, honestly, a graphical method at that point starts to look very appealing. But nowadays, if we have, hand calculators, or even if you don't even have a hand calculator, every cell phone has a sine function calculator built into it. So it's usually not worth you doing these methods. I'm including these more for the sake of completion. So the first method, graphical methods, you could just do, let's see, really just plotting them literally to scale, head to tail. I would maybe first plot F1 with theta 1 here. Then from that, off of the F2 axis, well, probably should have a head on that arrow. And then then I should plot the F2, maybe something like this. And that would be at whatever angle theta 2 is off of a horizontal axis I strike here, and that would be theta 2, and that would be theta 1. And then I would have theta 3, or F3, I should say, like this. And off of an x-axis with the origin at the end of F2, I could find a theta 3. And the net force on this object would literally be, if you're doing this via graphical methods, really all you have to do is just nothing more. If you plot these all by hand, if you plot them precisely, if you use an actual ruler to measure out a proportional distance, if you use a protractor to measure out a relatively precise angle, you can literally just take a straight edge and strike a line from the original origin right to F3. And that would be your F net. And the net force then will be your the length of that line, and the overall theta will just be the overall theta will be the length, the final relative angle. And that's graphical methods. All right, next let's consider the second method of polar vector summation, and that is the parallelogram method. And this can be done, thankfully, without using a protractor and a compass and a ruler. Well, I guess you could do graphical methods without the compass, but at least without the protractor and the ruler, and to scale drawings, which are a royal pain in the butt to use. But anyway, the second method is going to be the parallelogram method. So let's go ahead and label that to the parallelogram method. Or the triangular method, depending on your perspective. I have seen this labeled different ways or described different ways. The triangle method. Basically, especially this works very well for. This is optimized for basically two vector summations, summing two vectors. If you want to sum more than, wish to sum more than two vectors, you need to combine multiple instances or multiple applications of the parallelogram or triangle method. So the basic idea of this is, one, create a drawing. It doesn't have to be to scale, or I should just say a sketch, of the vectors lined up head to tail. Lined up head to tail. Two, apply trigonometry. So, for example, let's say you have two different vectors, A and B, acting on a single point. So, you have vector A, and I'm going to illustrate why this is referred to as the parallelogram method. A and B. I should probably put also step 3 here. Step 3, the diagonal of the parallelogram represents the resultant of the vector. The resultant of the vector. So let's say you have two vectors acting through a point, or acting on a point, or an object, or whatever it may be. You have vector A and vector B. So, and actually let me go ahead and label these as So they're not in, let me go ahead and mark these or create these, so they're not in such obvious or not such similar directions. So we'll get a nice true parallelogram. Maybe this is point O. So let us say we have a point O here. And first of all, let us go and define let's look what happens when we first put A and then B. If I first apply A, I would have something like this. And then if I put B head to tail on it, or tail to head on it, depending on your perspective, I would have something kind of like this. Actually, let me try to match the angle there. Not exact, of course, but that's what you get for hand sketches. B here. And then, what happens if I first put B and then add A? So B here. And then A. So you notice this forms a parallelogram. And the diagonal of this parallelogram represents the net vector, or the summation of these two individual vectors. So again, lining these up head to tail produces the net vector. And the really cool thing about this, I think anyway, is that it illustrates one of the basic properties of vector addition. You may remember a term from mathematics that is, and that term is commutative. Vector addition is commutative, or in other words, in vector addition, order does not matter. Order does not matter. It's just like regular addition. In other words, 2 plus 3 is the exact same as 3 plus 2. There are many mathematical operations that are not commutative. For example, 3 divided by 2 is not the same thing as 2 divided by 3. But vector addition is the same thing as regular addition, regular numeric, or I should probably say arithmetic addition. A plus B, or vector A plus vector B is equal to vector B plus vector A. These are the same no matter which way you're going. So how can I then apply this? I mean, how can I actually find that summation? Well, let's look at this. So let us say I have, let's actually look at this here. Let's blow this up a bit. My AB and BA. So let me do this in red again. So I have my AB and my BA. And my BA. And I'm sorry if this ends up looking like a rectangle. That is not my intention, but it's just meant to be a parallelogram. And this is the resultant. Maybe I could call this R. And this would be the resultant vector R. So the thing about this, and these may look a little bit like right angles, they're definitely not. I don't want this to be a rectangle. So if I know this vector, if I know everything about this vector initially, if I know about vector A and B, I know theta A right off the bat. And I also know theta B. And I also know theta B. So I know the orientation of this vector here. I know its angle. And in turn, I also, if I know the vector from here to here, I know this is equal to theta A. And if I know this here is theta B, then I know this is basically 180 minus theta B. And so look at this. Now I can just apply triangle properties in trigonometry, basically. If I have a triangle, I know the magnitude of A, and I know the magnitude of B, and if I know this here and this here, I know this combined angle, and suddenly I can just apply triangle properties or trigonometry. And I can apply either the law of sines or the law of cosines. Law of sines or law of cosines can be applied to solve this. Or law of cosines can be applied to solve this. Can be applied to solve. So, for example, the law of sines, if you don't remember, let me go ahead and draw this out for a triangle, a generic triangle. If you have a triangle with side lengths A, B, and C, A, B, and C, and then angles, let's say alpha, beta, and gamma, the law of sines states the following. That is simply that A over sine A, or sine alpha, is equal to B over sine beta. Sine beta is equal to C over sine gamma. Very simple trigonometry. Or I could also apply the law of cosines, and that is that C squared is equal to A squared plus B squared minus 2AB times the cosine of gamma. Again, this is just a very basic review from trigonometry, but even though we're not dealing usually with lengths here, unless we're dealing with displacement vectors, even though we're not dealing with lengths, we can just apply basic trigonometry, even to things like forces or things more exotic like electric fields, momentum vectors, and any other number of things. So the parallelogram method is very useful if you really if you want to directly sum your vectors in polar form, but we don't necessarily use it very much on an everyday basis. I tend to use, if I need to sum vectors generally, especially force vectors, I tend to use Cartesian more than anything, but it does have its uses. So we have that there. Maybe I can provide an example of this. Let's go ahead and work through an example. Let's work through a very basic example. Let's say I have two velocities that I want to sum. We could do that. We could do this in velocities. Why not? Let's see. Let's look. In fact, let me illustrate a actual full problem. So maybe the problem says something like a plane or a car or a person is walking at, let me say running at 7 miles per hour at an angle, let's say 25 degrees above the x-axis. They throw a ball. This would be a relatively small ball throwing velocity. I'm going to try to keep the two velocities relatively similar, but I will prephrase this saying this is kind of a ridiculously low velocity for a ball throw. So maybe they just barely managed to throw it or something. So they throw a ball at 5 miles per hour at an angle, let's say 30 degrees above the x-axis. And this would be the positive x-axis for both of these. Find the net velocity or the final velocity of the ball. The velocity of the ball with respect to the global x-axis or the global coordinate system. And I want to do this using the parallelogram method, or use polar vector summation. So that's what we're going to do, and I'm going to work through it on the next slide. So solution here. The first step is going to be to draw this out. So I have two things. I have two vectors, and I'm going to set these up head to tail. So the first thing I might do is to create my x and y axes. I have my, and in fact I can probably get away with not using any negative coordinates, or sorry, not drawing any negative quadrants, so I'll have only the first quadrant. So I'm going to have, let's say 7 miles per hour at 25 degrees above the positive x-axis. So I can just draw that as a 7. And then 25 degrees here. 25 degrees. And then 5 miles per hour at an angle of 30 degrees above the positive x-axis. So I can manage not to trip over my words. So 5 at an angle, a slightly larger or a slightly higher angle. 5 at an angle of 30 degrees. Now, I could go and also recognize this is a parallelogram, although it's going to be a fairly narrow parallelogram. So it's going to be something kind of like this. 5 and 7. And this is not quite to scale, of course. But what I really need to focus on is this triangle here. I'm going to need to apply trigonometry anyway, so I'm going to focus on this triangle here. So let's figure this out. Let's try to figure this out. What I really need to get is just a single angle. If I can figure out this angle, I can apply trigonometry for the rest of it. And, well, actually, did I give us a what we want? Yes, find the velocity of the ball with respect to the global coordinate system. So let's think about this. Maybe I'll do this in orange. If this is 30 degrees here, if this is 30 degrees, well, let's think about this. I know that if this is 25 degrees, then alternate interior angles, this is also 25 degrees. I know to the vertical, this is 90 degrees from here to here, a right angle. And I know if this is 30 degrees from here to here, then this is 60 degrees here. So that means the total angle here, nice obtuse angle, the total angle for this triangle is going to be 25 degrees plus 90 degrees plus 60 degrees. So that will come to a very large angle of, let's see, that will be almost 180, so that would really throw a monkey wrench in these, but that would actually be an incredibly large 175 degrees. 175 degrees. Oh my goodness. So that's an extremely obtuse angle, so I'm definitely not going to draw this to scale. That's okay. So we now have a triangle with the resultant force that we're looking for. So we have this here, our resultant force that we're looking for, and we have a triangle of length 7, or a vector of length 7 and 5. But then the angle is 175 degrees. So we need to find vector r. And we can do that. Now the most straightforward method of doing this is going to be, well, let's see. We could use, let's see, what could we do? Could we use the method of sines? Not without a bunch of algebra, so no, we're going to have to use cosines. I like to avoid the method of cosines if possible because it's a long and boring equation. It's kind of a pain in the butt, but actually in this case, that's going to be the simpler case. So I can say then that r squared is equal to, let's see, the a squared plus b squared, that's going to be 7 squared plus 5 squared plus, or actually minus, 2 times 7 times 5 times the cosine of 175 degrees. Isn't that lovely? So let's just throw this in a calculator and let it deal with the problem. So 7 squared minus, plus 5 squared minus 2 times 7 times 5 times the cosine of 175 degrees. There. 7 squared plus 5 squared minus 2 times 7 times 5, I'm just checking my calculator, times cosine of 175, and I get that r squared is equal to 143.7, 0.7, and r is equal to the square root of that, which is 11.99. Not unreasonable. 11.99. And actually that's what I would expect. For this obtuse of an angle, I would expect that length to be almost exactly equal to the summation. In fact, I might even indicate that this is 11.989, just to indicate that it's not just rounding to 12. But yeah, if this angle is that obtuse, I would expect it to be, the overall length of it should be about equal to the combined length, or the simple summation of 7 plus 5. 7 plus 5 is 12, so that's about right. Okay. So this is the magnitude of the combined vector, and the units for that would be miles per hour, since we're dealing with this in velocities or speeds, well, I guess velocities. Now, we should also go ahead and find the theta, and I can do this just by finding the, let's say, the theta here. If I know this theta, I can find the global theta fairly easily. So let's think about that. Again, if I know that, if I can find this theta here, I can find the global theta very easily. And I can do that just using the method of sines. Once I have this 11.989, the rest is basically cake. So I can just apply the method of sines that we discussed previously. And that would be, let's see, the sine of theta over 5 must be equal to the sine of 175 divided by r, which is 11.989. So that means the sine of theta, if I do 5 times, I'm going to throw in my calculator, 5 times the sine of 175 divided by 11.989, 5 times the sine of 175 divided by 11.989, and that's a very small value, so we're going to get a very small angle here. And this is 0.0363, 0.0363, and that's sine of theta, not just sine. 0.0363 is what I got. You might check that on your own. Make sure I didn't make any stupid mistakes, which is certainly possible. And then theta is equal to the inverse sine of this, inverse sine of 0.0363. And that comes to a modest, actually not as bad as I would think, as I would have thought, 2.08 degrees. Not too bad. So still something you could measure with a protractor if you wished. 2.08 degrees. So that means the angle from here to here is 2.08 degrees, which means, knowing that, I basically know that from here to here is 2.08 degrees, which means I can then find the overall global angle. And the overall global angle is just going to be, or the overall angle of this combined vector, actually, sorry, 2.08 is not from here to here, it's from the diagonal of the parallelogram to there. And so, but what I really want to report as my final answer is the theta that combines, that theta measured off of the x-axis. And so I just need to add 25 degrees to that. Oh, sorry about that. So I need to add 25 degrees to that. And so the overall theta, or the global theta, is just 25 degrees plus 2.08 degrees, or 27.08 degrees. So that means the resultant force, or I shouldn't say force, the resultant velocity from throwing the ball while walking for the original problem is going to be, that will be 11.989 miles per hour. 0.989 miles per hour at an angle of 27.08 degrees above positive x-axis. Or I could also report that as a global or absolute angle. Alright, let us next consider the final application of vector addition, or the final method of vector addition, and that is applying vector addition to Cartesian vectors. And we're going to do this using the component method. Again, we're going to do this using the component method. So, the two previous ones we discussed were most applicable, or really only applicable to polar vectors, vectors in polar or radial form. But for Cartesian vectors, we are just going to use the component method. And this one is fairly straightforward. And really, this is the one we tend to use the most in most engineering practice. It is the most convenient, especially if you already have your vector in Cartesian form. And especially in 3D problems, it's so convenient that, or so useful, that often I will convert, even for 2D problems actually, I'll usually just go ahead and convert things to rectangular just for the sake of using the component method. So, first of all, if the vector is in a Cartesian form, obviously the magnitudes cannot simply be summed. The magnitudes cannot be simply summed. Or you can't do some really weird combination of a 4-term Pythagorean theorem or something like that. Instead, we need to add the individual components and then recombine them together, reconvert them to polar form if we want that. Instead, we use the following, the steps. 1, add together the individual x and y components. Add together the individual x and y components. X and y components. Two, if the final vector is desired in polar, then just simply reconvert to polar. Simply reconvert to polar. So, for example, and this is actually one of those that's best illustrated by example, I think. So let us say I have two vectors. Let's say given vector A has components of maybe -3 newtons, so that would be 3 newtons to the left, and 5 newtons in the y, so 5 newtons upward, and vector B has components of 2 newtons upward, and maybe, let's say, -1 newton in the y, so 1 newton downward. Now, one way of saying this is I could say that the resultant x, the x component of the resultant vector, is going to be equal to ax plus bx, the x component of x plus the x component of b, or sorry, the x component of A plus the x component of B. So that would be equal to -3 newtons plus 2 newtons, or simply -1 newtons. And so that's the x component of the final resultant. And then our y would be the y component of the resultant. And that would be ay plus by. That looks a lot like a lambda, that's an x there. By, so that would be 5 newtons minus 1 newton, and that would then equal 4 newtons. And then if I wanted the final vector in polar form, well, first I could just say vector r in rectangular form is -1 newtons, comma 4 newtons. But I could then go and convert this to polar form using methods we've seen previously. And I could just go ahead and start by plotting that out. If I have my, let me go ahead and create a set of axes, x and y. And then maybe a different color, I'll go ahead and plot my magnitudes, or my components. So -1, or just 1 in that direction, and then 4 downward like this. And I'll have my resultant, and my theta. The magnitude of this, the magnitude of r, is going to be the square root of 4 squared plus 1 squared. Square root of 4 squared plus 1 squared. Let me throw that into my calculator. So that will be the square root of 17, or simply 4.12. And that would be newtons. 4.12 newtons, and then theta, that would be the inverse tangent, the arctan of opposite over adjacent, 4 over 1. The inverse tangent of 4 over 1, or the inverse tangent of 4, and in degrees, that will come to 75.96 degrees. Or I could say that the r vector is 4.12 newtons at an angle of 75.96 degrees below the negative x-axis. And that's fairly straightforward. But these systems can be quite more complex. Here, it looks like I've run out of slides, and I actually need to create some more slides for this lecture. So give me a minute here. Let me just go ahead and copy this one and paste, and we'll get a couple more slides to work with. I need to adjust my slide template here. Okay, so I've got some more canvas to work with. And then, if I were to go and illustrate a slightly more complex example, let's say I had a variety of forces, and these were defined as initially given in the polar form. How would I do this? Let's say I had a variety of vectors applied to a single point, maybe vector A, vector B, and vector C. So I had vector A, vector B, and vector C. And vector C. And let's say I had my x and y axes like this in the horizontal. Actually, let me relabel vector A. I don't like how it's almost horizontal here. And in fact, let me go ahead and make that even negative if I wanted to. Maybe A is down here. With A, and there's a theta A here, a theta B here, and just for fun, a theta C here. And so, if I wanted to find, let's say I wanted to find the net vector, the summation of all of these vectors, the first step will be to convert all of these into Cartesian form. I basically have them in rectangular form. I have their magnitudes, some magnitude A, like 2 newtons at an angle of 20 degrees below the horizontal or something. And as we've already discussed, we know how to find this, how to convert that polar form into rectangular form. So the first step is to convert the rectangular form into the polar, the polar form into the rectangular. Into rectangular. Then, so basically what I'm going to get is, I will then have vector A is equal to AX, comma AY. I will have vector B is equal to BX, comma BY. And I'll use my sines and cosines appropriately to do this. And applying, let's see, negatives, ay would have the vertical component, or the y component of a would be negative, and the x component of c would be negative. So then c, I would get its cx comma cy components. That would be the first step. 2, find the resultant in rectangular form. The resultant in rectangular form. If I can manage to write properly. And the resultant x would just be the ax plus ay, or not ay, sorry, plus bx plus cx. And the ry would be ay plus by plus cy. And then finally, if I wanted to get the actual, I could actually report the final resultant as just rx and ry, or I could just say, if I wanted to get this into polar, convert back to polar if desired. And we've seen how to do that. That's not really too bad. Convert back to polar if desired. If desired. So take your rx, comma ry, and convert that to a magnitude of r and a theta. And you would report that theta again as either a global angle, which would be measured off of the global x-axis, counterclockwise positive, or it would be measured as a reference angle off of either up or down, off of the either above or below the positive or negative x-axes. Okay, and that's the basic idea of vector addition. And vector subtraction is the other thing I wanted to discuss, but really this is very simple. Vector subtraction is very easy to get. Once you have, the hard part is vector addition. Once you have vector addition, vector subtraction is trivial. Vector subtraction if I can manage to spell subtraction properly, is just a modified form of vector addition. And we don't deal with vector subtraction very much in this course, but I should mention it for completion's sake. So I'm going to show how to do this, or describe how to do this for Cartesian. Actually, I can probably go ahead and describe them for both polar and rectangular forms. So basically, if I have a minus b, the key thing to realize is that this is just equal to a plus negative b. Fairly obvious if you think about this from the point of view of numerical or arithmetic subtraction, but how does this apply to vectors? The hard part is figuring out how to, since we already know how to sum vectors up, the hard part is figuring out how to find this negative b. Well, rectangular is easy. To get negative b, simply apply the opposite sign to the components. Simply flip the sign of the components. Of components. If b equals, for example, if b equals 2 newtons, comma, negative 3 newtons, then the negative b that you'll add to a, then negative b is just negative 2 newtons, comma, positive 3 newtons. Very simple. Polar form is also not too bad. With polar form, all you do is rotate the angle of the vector 180 degrees. The angle of the vector 180 degrees, and you're going to be using trigonometry anyway if you're dealing with the polar form, so that's not too bad. The angle of b by 180 degrees. So if you're, let's say you had a coordinate system here, x and y, if your original B was, let's say, in the first quadrant, B here, at an angle of, say, 30 degrees, well, the negative B would be down here. Would be the negative B at an angle, a global angle, for example, of 210 degrees. You just rotate it, you keep the magnitude the same, but rotate it 180 degrees, and then simply sum the vectors, the negative B vector, as you would otherwise. Alright, so that'll do it for this portion of the lecture. I know this is kind of a long lecture. We did have a lot of material to go through, but this should serve as a very useful introduction to covering the basics of vectors, the very basics of vector summation, at least for 2D. We'll save 3D for lecture 3. But this does cover the very basics and the very elementary concepts of vector summation, vector addition, what a vector is, and also forms of vectors versus polar and rectangular, scalar versus vector, and all these things. So I hope you learned a few things. I hope you found this at least tolerable, if not enjoyable. Enjoyable preferably, but at least tolerable. I know this is fairly dry material, but it is something we need to cover as we work through our course. So if you have any questions, feel free to let me know. If not, I will see you soon in the next lecture of the course. Again, hope you all enjoyed this. Hope you all learned a few things. I will see you all again soon for lecture 3. And as always, thank you.